Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is electromagnetic induction and Lenz's law. To let you know roughly where we're heading with today's video, consider the following. When we started this unit, we looked at how electrical currents produce magnetic fields. If you think back to right-hand rule number 1 and right-hand rule number 2, that's what I'm talking about. It seems natural to wonder if electrical currents can produce magnetic fields, then can magnetic fields produce electrical currents? Well, that's the question that we're going to answer in this video. And so what I'd like you to do is, in a moment, pause the video, have a look at some of the other questions we'll answer, take a look at where we are in the unit schedule, and also the learning goals and success criteria. Please do that now and then come back. All right, you're back, and here we go. Let's get started. First off, without really having you in class to show you a certain demonstration, it's kind of hard to do this in a way that makes it, that has that sort of wow factor. However, luckily for us, PhET, remember these guys, have a good simulation that you can use to give you an idea of what you're going to see in class. So you're going to go to the PhET website. I'll go there now. And I'd like you to click on Physics, go under Electricity, Magnets, and Circuits, and you're going to find Faraday's Electromagnetic Lab. Download that. It's free. It won't introduce any viruses onto your system, and when you run it, you're going to see something like this. Now, there's a number of tabs across the top. The one that we're looking to start at is Pickup Coil. So go to this. I think when you start, I'll hit Reset All. Let's say yes. It starts off like this. You see a magnet. You see some compass needles, which kind of fade as they get farther away from the magnet. These are showing you the magnetic field. There's also a coil, or a helix, connected to a light bulb. What I'd like you to do is switch the light bulb for a voltmeter by clicking on this button right here. Also, we don't really need to see the field. It's a little distracting, so get rid of that. And at this point, you're pretty much set to answer the question that I asked you a moment ago. If electric currents can produce magnetic fields, then is the reverse true? Can magnetic fields produce electric currents? If this magnet can produce an electric current, then we are going to see the voltmeter's needle deflect one way or the other. Now, here's a button that is worth pointing out. You can either show electrons or not. I just have to warn you, if I click Show Electrons so that you can see whether a current is flowing, please remember, in grade 11 and on, we don't define current as the direction of electron flow. We denote it as the direction of some hypothetical positive charge flow, which of course is in the opposite direction of electron flow. Most scientists do it this way, and so we're just using the standard method. However, it is really the electrons that are moving, so a little bit of a tricky situation there. I'll keep them on just to emphasize the fact that we want to see whether current is flowing, but do remember this will show us the opposite of what we've been studying in class. Anyway, back to the question. Can a magnet induce a current to flow the same way a current can produce a magnetic field? Well, the simulation doesn't really seem to have a start button here, so that means it's on, it's running. Do you see any evidence of a current flowing? The answer, of course, is no. And I'm going to show you a simulation or a demonstration of this in class. I'm going to take a helix or a coil, and I'll connect it to actually not a voltmeter, but something called a galvanometer, a very sensitive ammeter. And when the magnet is just sitting there, you will see there is no current flowing. And then what I'm going to do is I'm going to start moving the magnet. And all of a sudden, you'll start noticing that the needle deflects. The slower I move the magnet, the less deflection you get. The faster I move it, and the closer I move it to the coil, the more you notice the electrons moving. Other things, if I move the North Pole in, the needle goes that way. But if I move the North Pole out, the needle goes the other way. Show that to you again. North Pole in, needle goes left. North Pole out, needle goes right. So a couple of other things I can do. I can increase the number of loops, and now what do you notice? If you watch how much the needle's deflecting, now let me compare it with just one loop, you'll notice that with more loops, you get more deflection of the needle. This is probably better shown if I replace the voltmeter now with a light bulb, because you're going to see the light bulb goes on when I move the magnet. If I have more loops, I get a brighter light bulb. And also if I move slowly, I get a little bit of light. But if I move rapidly, I get a lot of light. So what is this telling you about magnets and electricity? Pause the video now and see if you can jot down a few observations or summaries of what was happening, and then we'll discuss. All right, you're back, and let's see if we can figure it out. First of all, it's not a magnetic field that causes a current. It's a changing magnetic field that produces a current. If the magnetic field through the loop or the coil changes, that's what causes the current to flow. So maybe now it's worth showing the magnetic field, and you'll see that as I move the magnet around, of course those compass needles will move, showing that the field is changing. As I change the field through the coil, I get the current. The more loops there are, the higher the current, and also the slower I move the magnet and change the magnetic field, the less current I get. The more rapidly I change the magnetic field, the more current I get. So now let's go back to the sketching program here and see if we can relate that idea to the original experiment done by Michael Faraday, an English physicist back in the 1700s or 1800s, who first noticed this going on. Now Faraday didn't use a permanent magnet, a bar magnet, and a loop. What he did was he used an electric circuit. So this is an image from your textbook, Physics 11 by Addison Wesley, and you need to kind of examine this to get an idea of what's going on. He starts off with what's called the primary circuit. Primary, or number one. He's got an electric circuit. It's connected to a power supply, and that voltage is shown by V1. There's a switch here, which if it's open, of course, no current flows, and if it's closed, a current will flow. So this primary circuit is wrapped around an iron ring, which also contains another circuit. This is called the secondary circuit. So number two. And this one is similar to the first one. It doesn't have a switch, but it does have a galvanometer. A galvanometer is a very sensitive ammeter. If any electrical current is flowing in the secondary circuit here, the galvanometer will show. If the current flows in the positive direction, the needle will go to the right, and if the current flows the other way, it'll go to the left. There is a resistor here so that we can measure the potential difference. And if you look back at this screenshot here from the PhET simulation, basically this resistor here represents that resistor, or you could replace it with a light bulb if you click on this button. It doesn't really matter. The idea is the same. They don't show an ammeter here the way the picture in your textbook does, but this will just show us the actual current flowing. What PhET does instead is they show you the electrons, which we already saw were moving. So what did Michael Faraday notice? Well, first of all, I think it's pretty obvious. You'd probably realize this right away. If the switch is open and there's no current flowing in the primary circuit, he notices nothing, no current flowing in the secondary. If he closes the switch and a current begins to flow in the primary, of course it goes from the positive around to the negative, then if he does that, all of a sudden the needle moves ever so slightly. But then after he keeps the switch closed for a moment, the needle here goes back to 0. So what is that all about? Well, let's go back to the simulation. If I just keep the magnet sitting there, nothing happens. If I move it, there will be light, but if I stop moving it, there's no more light. Or if you prefer, there's no more current, right? The needle only moves when the magnet is moving. So how does Faraday explain this? Well, remember, when there's a current flowing in the primary circuit, that means over here, where we have a helix, think of right-hand rule number 2, there will be a magnetic field through this helix. The iron ring, any piece of iron can redirect the magnetic field around to this side, because iron's a ferromagnetic substance. So what ends up happening is by having a magnetic field in this coil, you end up getting a magnetic field in this coil. Again, right-hand rule number 2, will show you where the North Pole and the South Pole is in this helix. Now, remember the observation back here with PhET, that you only get that current when the magnetic field caused by this bar magnet is moving or changing. Well, that would explain why when he closes the switch, you get a brief spike in the current. That's because you have changed the magnetic field from 0 to greater than 0. However, once the switch has been closed for a while, there is no more change. And because there's no change, it's like having this magnet just sit where it is. There's no current flowing. That's why the needle goes back to 0. Now, another thing that's interesting is when Faraday opened the switch to stop the current from flowing in the primary, now he noticed that the needle deflected again, only it did it in the opposite direction to what it did when he closed the switch. Why did it do this? Well, when he opens the switch, the magnetic field goes from greater than 0 back to 0. In other words, it changes. And therefore, that changing magnetic field is redirected through the secondary helix, and that leads to a change, which is the same as moving this magnet in the PhET simulation. So Faraday's setup is really just the electric circuit version of the PhET simulation. Okay? Couple of terms to point out. We've already talked about V1 and V2, the potential differences in the primary and secondary circuit. There's also this term here, or this variable N1 and N2, which are the number of coils, literally just how many times did you wrap the wire around each helix, 1, 2, 3, 4, and so on. He notices a relationship, which is that if N1 is smaller than N2, in other words, there's more turns in the secondary coil, then the voltage across the secondary circuit is higher. In other words, there's a ratio. You can write the formula V1 over V2. The ratio of the two voltages is actually related to the ratio of the numbers of turns. More turns gives you a higher voltage. You can actually use this first circuit with a lesser number of coils and the second circuit with a greater number of coils to increase voltage. Sounds kind of like getting something for nothing, doesn't it? Well, as we know in life, you don't often get something for nothing. Well, you don't get something for nothing here either. We're going to learn later on in the video what it is you lose if the voltage goes up. All right, moving on. So now we're going to look at something called Lenz's law, and this is where we're going to see the fact of the video. Lenz is another scientist who comes up with a way of figuring out what direction the current flows, because if you think back to the PhET simulation, there was a little bit of some detail that I didn't mention here. If the North Pole is brought close to the coil, watch the direction of the deflection of the needle. The needle goes to the left. But if I pull that same magnet out, now the needle goes to the right. Now, what if I do the following? What if I move the coil over here and now I do this? Now I've got the South Pole over here. I'm going to insert a South Pole. What do you think is going to happen to the needle? What direction will it go? The needle goes to the left, and when I pull the magnet this way, the needle goes to the right. So can you see that it actually matters not only what direction is the magnet moving, but also which pole is being inserted or removed. So getting back to our discussion here about Lenz's law, these two diagrams, also from your physics book, will explain what direction the current flows based on what you do with the magnet. In the first diagram, the North Pole, as indicated by this arrow, is being inserted. The light bulb goes on, which means a current is flowing. The textbook tells you that the current is given by the direction of these arrows. So what are you going to do? You're going to use right-hand rule number 2, which, if you recall, has your fingers in the direction of current. So make sure your fingers are pointing up and around this helix here. And that means your thumb will point to the North Pole, which they show you right here, which also, by the way, means the South is there. So the book is telling you here, and again, we will see this when we do this demo in class, that if the North Pole is inserted, a north pole results here due to the current I, which flows there. What about if you remove the north pole as indicated by this arrow? The north pole is now being removed. Now the book tells you that the current goes the other way. Take your right hand and make your fingers point down, okay? However, they have to be pointing down on the front side of this solenoid. So the way to do this is the following. If you've got something cylindrical, it could be a pencil, a pen, a can of Coke, whatever, anything. Hold it in front of you the way this helix is oriented, and take your right hand and make your fingers point down, but not behind the object, in front of the object, because these wires and these arrows are on the front side, the side facing you. Your thumb should be pointing to the right, which is where the North Pole is, which means that a South Pole is here. So once again, these are what actually happen if you move the magnet in the way that's indicated, and if you look at the current direction using an ammeter or a galvanometer. You'll see this in class when I do it. Here's the question. Why does it happen? And can you figure out a rule for predicting what is, what is the, I guess, what is the relationship is what I'm trying to say here. Well, let's think. When a North Pole is inserted, a North Pole greets it. When a North Pole is removed, a South Pole sort of comes over there to watch what's going on, see the North Pole going away. This north to north is an example of repulsion. This north to south is an example of attraction. Does that give you any hints? Here's a little more information. When a North Pole is inserted, a current arises or is induced which repels the incoming North Pole. However, when a North Pole is removed, a current results, current is induced, which causes a South Pole to try to attract back that North Pole. What is the solenoid, what is the helix trying to do? If you were to summarize it, you could say that the current and its associated magnetic field is trying to oppose the change. If you can remember these three words, oppose the change, you'll be able to predict what direction the current flows. Once again, here a north is being inserted, so a current arises. The direction of that current is such that, according to right-hand rule number 2, the magnetic field opposes the incoming magnetic field through repulsion. Here the reverse is happening. A north is being removed, so a current results, which leads to a magnetic field, which is such that it will try to attract or oppose the change that is occurring. All right? That is Lenz's insight, is that he realized that induced magnetic fields will oppose the change that created them. And of course, remember, where does the induced magnetic field come from? It comes from the fact that there is an induced current. So I guess I could go one step further back in the chain here. So induced currents cause induced magnetic fields, which oppose the change that created them. What induces the current? Again, back to the PhET simulation, changing magnetic fields induce currents. So we could go a step further back here. Changing magnetic field induces a current, which induces a magnetic field which opposes the change that created it. The greater the rate of change, the greater the induced current and magnetic field. So a question might be, why doesn't the current flow the other way? Why doesn't the changing magnetic field, which is this, induce a current, which is this? which induces a magnetic field, which is these, that doesn't oppose, but rather creates more change? Well, here's the answer. If you try to imagine the reverse situation happening, which is shown in this diagram, for example, a north pole being inserted, if the current were to flow the other way, try right-hand rule number 2 here, you'll see that what's happening is a south pole is being created at the left. A south pole would attract the incoming north pole, so that instead of opposing the change, it would actually create more change by getting the magnetic field to change faster. This would lead to a greater induced current, which in turn would lead to a stronger induced magnetic field, which in turn would pull this magnet in even faster with greater attraction. Can you see how this would be a runaway process? What we would basically be faced with is a situation where if you just gave this magnet a little push to begin it moving, if you did a little bit of work on it, exerting a little bit of force through a little distance, all of a sudden we would get a lot more kinetic energy as the magnet got attracted inward and began moving faster. And of course here we'd get a whole lot of light and heat energy. In other words, for a little bit of input energy on our part, we would get a lot more output energy. We would actually violate the law of conservation of energy. This is why Lenz's law is the way it is. The induced magnetic field must oppose the change that's occurring it to avoid violating the law of conservation of energy. All right, moving on. So let's look at an application of this situation where we know that a changing magnetic field creates an electric current. If you're in my class and you've been with me for a while, you've probably seen this demonstration on numerous occasions. It's a hand crank generator. These are seen from opposite sides. On one side you have a handle on a wheel, and that's attached by an elastic band to what you see here, which is a coil of wires near what turns out to be a magnetic field shown by the north and south. And for those of you who have seen this in class, as I turn this, I convert the kinetic energy of the wheel into, there's a little light bulb here, which is kind of hard to see in the diagram, but here the light bulb actually goes on. And if we want to connect a meter like a galvanometer to these leads here, we can measure the electric current. All right, so what's going on? Well, here is the magnet, and the magnet is actually sitting still. So it's not quite like the PhET simulation where I was moving the magnet and inducing a current. Instead, what we do here is we move the coil, but the result is the same. Does the simulation show this? Yes, if I move the coil around, even that causes the needle to deflect. I'll show it to you with a light bulb. It's a little bit easier to see that way. You don't have to move the magnets. You can if you want. All that matters is that the magnetic field shown by these compass needles changes through the coil. So in an AC generator, what we do is we take, here's a diagram from your book by the way, we take a coil here with obviously the wires wrapped around it, and we connect them to a voltmeter, or as you're going to see, we connect it to the power grid so that we can send electricity to consumers. All we do is spin that rotor, as it's called, or an armature is another word for it. And if you care to take a look at this diagram in more detail in your book, you'll see exactly what's going on. I'll give you a little bit of a hint to get you started. They show you the north end of the magnet and the south end, and you're turning this. This arrow here shows that the direction of turning is clockwise. So what's going to happen? Well, one end of the coil over here is going to be approaching the north end of the magnet. So what does Lenz's law tell us? It tells us that this end will become north to oppose the change that is occurring. As it passes that magnetic pole, it is now going away, and now the change is that this end is going away from the North Pole, therefore it becomes south to attract itself back to oppose the change. Meanwhile, on the other side, this end of the magnet here is coming toward the South Pole of the permanent magnet, and therefore there will be opposition to that change, so we get a south. A little while later, this end is going away, so now we get a north to attract it back, to oppose the change once again. That's Lenz's law. So you can also see from the voltmeter that the current reverses direction, and eventually it switches from 0 to positive, back to 0, to negative, back to 0, and so on. In other words, we have alternating current, as opposed to direct current, such as you get in a battery. Now, how are we going to make practical use of this? Well, I guess we could sit there and crank the generator with our hand, but that really wouldn't be very effective. If we had a whole bunch of people in a room cranking these in order to generate electricity, don't forget we'd have to feed them a lot of food because they would be burning their own calories. We would probably end up spending more energy in terms of feeding them than we would get back in terms of the electrical energy. So we got to get something else to do the turning. What is that something else? Well, it could be wind and a windmill. It could be water and a water wheel. It could be the steam generated when we boil water by burning coal. That steam under high pressure could turn this coil. And that is actually how we generate electricity. If you think back to a previous video, I talked about how a hydroelectric power plant works, and I briefly touched upon how a fossil fuel plant works. And I believe we've also talked about things like windmills. So anyway, you've seen the connection here now, and you can also explain the physics of why the current is doing what it's doing. It's really Lenz's law and electromagnetic induction. Okay, so now that we know that we have an alternating current, we have an interesting situation, because if you think back to electromagnetic induction, shown in this diagram, remember we had a primary coil and a secondary coil, and we learned a relationship which we're going to need to borrow in a moment. So actually what I'm going to do is copy and paste this one onto this slide here, just to remind you that in the primary circuit and the secondary circuit, there is a relationship between the voltage and the number of turns. This leads to a piece of technology that's called a transformer. A transformer is an electrical device that I'm sure you've seen before. Here are two pictures from Google Images. Transformers hanging from a hydro pole, or perhaps a transformer station. I'm sure you've seen these at the side of the road. Here's what happens. We take our familiar iron ring, we wrap the wires around one end, and this is called the primary coil. It's got NP as the number of turns in the primary coil, and the voltage is VP. Now, as we've seen from this formula right here, if there are more turns in the secondary coil, the voltage will be higher. So your textbook diagram shows you N secondary is greater than N primary, if leading to V secondary being greater than V primary. All right? Or we can do the reverse. We can have more turns in the primary than in the secondary, and therefore the voltage in the primary will be higher than the secondary. However, remember back here, I asked you, does it seem like we're getting something for nothing? We're just increasing the voltage by wrapping more wires around here? How can that be? In life, in nature, you rarely get something for nothing. You usually have to pay for things. Well, same thing goes in nature and with electricity and magnetism. What do you have to pay with here? Well, don't forget that while this formula may be true, there's another formula that we have to remember in an electric circuit, and that is the power in the circuit, which, if you recall, is voltage times current. Now, if we use this idea, we can do the following. We can calculate the the power in the primary coil. So I'll call that P primary is equal to voltage in the primary times current in the primary. Now remember also that power is energy times time. That comes from the formula power equals energy, over time, not times time. My mistake there. So I'll delete that and put in energy over time. Okay, so this will be equal to the voltage in the primary times the current in the primary. Now we also know that the power in the secondary coil is equal to the voltage in the secondary coil times the current in the secondary coil. And so we can also write that the energy in the secondary coil divided by the time that we measure that energy is equal to the voltage times the current. Now, we know the law of conservation of energy tells us that energy can't be created or destroyed. So we know that during equal time intervals, in other words, I'm going to cancel out these time considerations because they'll be the same for both coils, the energy in the primary should equal the energy in the secondary, which means that this is equal to this. So what do I have now? V in the primary, I in the primary, equals V in the secondary, I in the secondary. I also know this equation here, which relates the number of turns. So what do we do now? What we do now is we can either bring in this formula, or if you want to just give me one moment first, we do V primary divided by, now I'm going to divide this side by V primary, sorry, by I primary. Give me a sec here. No, I'm just kidding. I'm going to divide it by V secondary. Sorry about that, guys. That's going to cancel out the voltage on the other side here, and I'm going to get Vp over Vs. I'm also going to divide both sides by Ip, so that this cancels with that, and that's going to leave me with Is over Ip, like this. Now let me highlight that so I have this equation here, and I'm just going to copy this and paste it in up top. Okay, now I've got what I want you to look at. A couple of quick things. Remember, P primary is the same as the number 1, and S secondary is the same as number 2. So I could write this as the 1 can be primary, the 2 can be secondary. The 1 is primary, the 2 is secondary. So what do you got here? You've got two equations, one of them telling you that if you wrap more turns in the secondary circuit, you get a higher voltage. But what is this telling you? It's telling you that the ratio of the voltages is opposite to the ratio of the currents. So if the primary voltage goes higher, then what happens to the primary current? It is going to go lower. And the reverse is also true. So let's take a look at the bottom here. We'll notice that in this kind of transformer where there's more turns in the secondary, you have a greater N value, you have a greater V value, but you have a lesser current value. So if the voltage goes up, which is what we call a step-up transformer, then the current goes down. In other words, back here where I asked you, can you just increase the voltage as much as you want? Can you get something for nothing? No. You can have a higher voltage, but you have to pay for it with a lower current. All right? So these are called transformers. They're electrical devices that use electromagnetic induction to change the voltage at the expense of current, increasing the voltage at the expense of current, or decreasing the voltage and getting a higher current. Step-up transformer, higher voltage. Step-down transformer, lower voltage. And so finally, why would you ever want to do this? Why do you ever need to step up or down the voltage? I'm sure you can think of some examples in your home where there might be something you got to plug in, like a laptop, for example, or your smartphone charger. And the voltage, when you plug into your wall, of course, is 120 volts. That leads to a very high current, maybe so high that it'll damage your computer or your smartphone. So maybe we need to step down the voltage. Well, there will be a transformer built into your phone which will drop the voltage. But why would we ever need to step up the voltage? Maybe you can think of an example in your home where you need a higher voltage. A good example is a television, for example, which may operate at a higher voltage, especially the older televisions that use what's called a cathode ray tube. There, 120 volts is not enough, and we got to increase it. However, there's an even more important reason, which is shown in this final diagram in your textbook. Start off with the generation of electricity from the power plant. We've already looked at how this can happen. The electricity is generated, they say in the book, in the low tens of thousands of volts, so 18 to 24 kilovolts, they say. Now, a transformer steps up the voltage to 500,000 volts, 500,000 volts, which sounds like a lot. You know these transmission towers that you see throughout the countryside and in various places throughout the city. They are, believe it or not, at 500,000 volt potential difference, which is a very high number. Why so high? Is it because the power company is trying to show off? No, there's actually a very good reason for it. We'll get to it in a minute. As you near the city where electricity is going to be consumed, the first transformer station that you get to, which might look something like one of these, starts stepping down the voltage. So we have this step down. Now follow the diagram around to this side. Now you get to another transformer station where the voltage steps down again. So where have we gone from 500,000 volts to about 250,000 volts, now down from 250,000 to maybe 20, 30,000 volts. We step down again, and now we're into the 4,000 volt range. And then they show you maybe 600 volts for a factory where there's some high voltage equipment. Or as we head to your home, we're getting down to what I was telling you before, the 120 volts when you plug into the wall. There's also another circuit in your home used if you have an electric stove, which is at 240 volts. Also, if you have an electric dryer for your laundry, it may also operate at 240 volts. These are very powerful devices. They have large heating elements and they do need the higher voltage. However, why go to all this trouble? Why did the power company step up to 500,000 volts only to step back down to a few hundred volts? Well, the answer is shown very nicely in a sample problem which is in your book. And they do such a good job, I've decided to just copy and paste it in and let you follow along. Let's have a look. Electrical power is generated at a potential difference of 20 kilovolts, and then it is supplied to a town requiring 1 megawatt. So that would be 1 million watts of power required. All the people using all of their electrical devices require 1 million joules of energy a second. The transmission line along which the electrical energy flows has a resistance of 0.5 ohm. So this is the wiring, for example, that you see here, 0.5 ohm of resistance. How do the power losses due to heat in the line compare if they transmit the energy at 500 kilovolts instead of 20 kilovolts? So remember back here, power company goes from approximately 20,000 volts at which they generate the electricity up to 500,000. What if they just kept it at 20,000? That's what this question is asking you. So the given information, the voltage is going to be either 20 kilovolts or 500 kilovolts. The power required is 1 megawatt, and the resistance of the wires used in here is 0.5 ohm. And what they're asking us to figure out is the power loss, which they symbolize as P with a subscript L. Now, first off, where does this formula come from? P equals I squared R. Well, if you recall, from the formula for power, which is VI, and also from Ohm's law, which is V equals RI, if we sub this into there, then we get P equals RI times I, which is I squared times R. Okay, so remember that, that's where that comes from. And of course, here's the familiar P equals VI, so I equals P over V. So they do two solutions here. For 20,000 volts, what they calculate is the current that will be running through the wire if the town using 1 million watts gets their power at 20,000 volts. And you see that the current will be 50 amps. Okay? Now, how much power is lost when a current of 50 amps flows through a wire whose resistance is 0.5 ohm? They run through the calculation and you get 1.2 kilowatts, which doesn't sound like much. 1,200 watts of power is lost. That's the rate at which energy is lost due to heating of the wire, because remember, wires get hot when current runs through them. More current, more heat. However, if you replace this calculation, instead of at 20 kilovolts, if you sub in here 500,000 volts, which is the other option for transmitting the electricity, what you find is that the current gets much lower. In fact, I'm going to ask you now to do this calculation. I'll do it myself. See what you get for the current. All right, and what did you get? You should have got 2 amps, which is a much lower current when the voltage is higher. Now, where have we seen this before? Higher voltage gives you lower current. We've seen it here in the transformer, where stepping up the voltage by having more turns, higher voltage but lower current. All right, the current in the primary is higher than in the secondary. Well, this is like a secondary compared to where we generated the electricity at the primary. So by having a lower current, what ends up happening is the wire doesn't heat up as much. If you calculate the power lost here, it's going to be I squared times R. That's going to be 2 amps squared times a resistance of half an ohm. It's going to be 4 times half is just 2, which is what they show you down here. So the electric company is actually being very smart about this. They're transmitting at a higher voltage increase, so that the current will decrease. There will be less heating in the wire, less energy lost, more efficient transmission. But there is still loss that occurs, and you will come to know this very well when you have your own house or an apartment or a condo where maybe you have to pay for the electricity, because at the bottom of your electricity bill, they're going to show you how much energy you used in kilowatt hours during any given billing period. Suppose you use 1,000 kilowatt hours of electricity during a billing period. And suppose electricity costs 10 cents per kilowatt hour. You might be thinking, oh, okay, well that's not too terrible. I guess I got to pay about $100. However, there's going to be something called the loss adjustment factor. And what they're going to do is they're going to multiply by about 1.04. It's right on my bill. I can, if I had it with me in class, I would show it to you, but you can look online at a sample bill and you'll see this. They multiply by 1.04, so that actually your cost goes up to $104. Now, it might not sound like a lot, but I guess if you use a lot of electricity, over the years it does mount. What they're doing is saying, okay, you consumed 1,000 kilowatt hours of energy, but we know because of these losses, to get that 1,000 kilowatt hours to you, we must have sent more energy. And so they adjust upward your bill. I guess it's fair, it's physics, and that is the end of the lecture. Thanks guys, I will see you in class.